NENOMATICA, where mathematics meets YouTube excellence. Exponential Inequalities. Welcome to our math tutorial. Today, we'll explore how to solve inequalities using transformations based on finding common factors between terms. This is a powerful technique for simplifying and solving certain types of inequalities. Let's look at a practical example to demonstrate this concept. Example: let's solve the following exponential inequality: x squared times 5 to the power of x minus 5 to the power of 2 plus x is less than or equal to 0. First, let's rewrite this problem. We need to expand 5 to the power of 2 plus x. Using the laws of exponents, we can rewrite this as 5 squared times 5 to the power of x. Now, we calculate that 5 squared equals 25. So we have 25 times 5 to the power of x. Multiplying 25 and 5 to the power of x, we get 25 times 5 to the power of x. Let's factor out the common term 5 to the power of x from both terms. It's important to note that 5 to the power of x is always positive for any value of x. This is because 5 is positive, and any positive number raised to any power remains positive. Since 5 to the power of x is positive, we can divide both sides by it without flipping the inequality sign. This gives us x squared minus 25 is less than or equal to 0. Rearranging, we get x squared is less than or equal to 25. Taking the square root of both sides, we get the absolute value of x is less than or equal to 5. Therefore, negative 5 is less than or equal to x, which is less than or equal to positive 5. We can write this as our solution in interval notation as the closed interval from negative 5 to 5. Example: let's solve the following exponential inequality. We'll start by rewriting each term using the laws of exponents. Remember that when we have an expression like 2 to the power of x plus 2, we can rewrite this as 2 to the power of x times 2 squared. Next, we'll compute the values of each power. 2 squared equals 4, 2 cubed equals 8, and 2 to the fourth power equals 16. Similarly, 5 to the first power is just 5, and 5 squared equals 25. Now we can multiply the coefficients with the powers to simplify our expression. This gives us 4 times 2 to the power of x, minus 8 times 2 to the power of x, minus 16 times 2 to the power of x, which is greater than 5 times 5 to the power of x, minus 25 times 5 to the power of x. Let's factor out the common terms. We'll take 2 to the power of x as a common factor on the left side, and 5 to the power of x as a common factor on the right side. Now, let's calculate the expressions inside the parentheses. On the left, we have 4 minus 8 minus 16, which equals negative 20. On the right, we have 5 minus 25, which equals negative 20. We can simplify this by writing negative 20 times 2 to the power of x is greater than negative 20 times 5 to the power of x. Now, let's divide both sides by negative 20. When we divide by a negative number, we need to flip the inequality sign. So our inequality becomes 2 to the power of x is less than 5 to the power of x. To solve this inequality, we'll divide both sides by 5 to the power of x. This gives us 2 to the power of x divided by 5 to the power of x, which is less than 1. Notice that the fraction 2/5 is less than 1, so when we raise it to the power of x, we need to consider what happens for different values of x. When x is 0, 2/5 to the power of 0 equals 1. For any fraction between 0 and 1, like 2/5, raising it to a positive power makes it smaller. We know that any number raised to the power of 0 equals 1, so our inequality becomes 2/5 to the power of x is less than 1. Since 2/5 is less than 1, this inequality is satisfied when x is greater than 0. Therefore, our final answer is x is greater than 0, which we can write as x belongs to the interval from 0 to positive infinity. Welcome to this mathematics video. Today, we're going to solve inequalities involving exponential expressions of the form f of a to the power x is greater than or equal to 0. To solve this type of inequality, we'll use a substitution technique. We'll substitute t equals a to the power x, which transforms our exponential inequality into a simpler form. This transforms our original inequality from f of a to the power x is greater than or equal to 0 to f of t is greater than or equal to 0. This is much easier to solve since we've eliminated the complicated exponential. However, there's an important constraint we need to consider. since t equals a to the power x, and assuming a is positive, t must always be positive. This gives us our first inequality, t is greater than 0. So our original inequality f of a to the power x is greater than or equal to 0 transforms into a system of two inequalities. T is greater than 0, and f of t is greater than or equal to 0. Let's work through a specific example to demonstrate the technique. Suppose we want to solve the inequality. 2 to the power x minus 3 is greater than or equal to 0. Step 1. Let's apply the substitution t equals 2 to the power x. This transforms our inequality to t minus 3 is greater than or equal to 0. Step 2. Now we set up our system of inequalities. We have t is greater than 0 since t equals 2 to the power x, and t minus 3 is greater than or equal to 0 from our substitution. Step 3. Let's solve this system of inequalities. From t minus 3 is greater than or equal to 0, we get t is greater than or equal to 3. Step 4. Now we can simplify this system. Since t is greater than or equal to 3, and 3 is clearly greater than 0, the condition t is greater than 0 is automatically satisfied. So our solution is simply t is greater than or equal to 3. Step 5. Finally, we need to go back to our original variable x. Since t equals 2 to the power x, and t is greater than or equal to 3, we have 2 to the power x is greater than or equal to 3. Step 6. Now we solve for x. Taking the logarithm base 2 of both sides, we get x is greater than or equal to log base 2 of 3. Therefore, the solution to our original inequality, 2 to the power x minus 3 is greater than or equal to 0, is x is greater than or equal to log base 2 of 3, which is approximately 1.585. Let's try another example to reinforce this technique. Consider the inequality. 3 to the power x squared minus 2 times 3 to the power x plus 1 is less than or equal to 0. Step 1. Let's substitute t equals 3 to the power x. This transforms our inequality to t squared minus 2t plus 1 is less than or equal to 0. Step 2. Let's recognize that t squared minus 2t plus 1 can be factored as t minus 1 squared. Step 3. Now we need to analyze when t minus 1 squared is less than or equal to 0. Since a square is always greater than or equal to 0, the only way t minus 1 squared can equal 0 is when t equals 1, and it can never be less than 0. Step 4. Solving t minus 1 squared equals 0, we get t equals 1. Step 5. We need to set up our system of inequalities. We have t is greater than 0 as our first constraint since t equals 3 to the power x, and t equals 1 from solving our quadratic. Step 6. Let's check if our system is compatible. Since 1 is greater than 0, the condition t is greater than 0 is satisfied when t equals 1. So our solution for t is t equals 1. Step 7. Now we need to back substitute to find x. Since t equals 3 to the power x and t equals 1, we have 3 to the power x equals 1. Step 8. Solving for x, we get x equals 0, since any number raised to the power 0 equals 1. Therefore, the solution to our second inequality, 3 to the power x squared minus 2 times 3 to the power x plus 1 is less than or equal to 0, is x equals 0. Welcome to our math tutorial. Today, we're going to solve an exponential inequality. Let's solve the exponential inequality 4 raised to the power of negative x plus 1/2 minus 7 times 2 raised to the power of negative x minus 4 is less than 0. We can use the property of exponents that says a to the power m times a to the power n equals a to the power m plus n. So 4 to the power negative x times 4 to the power 1/2 equals 4 to the power of negative x plus 1/2. Now, let's simplify this expression. First, note that 4 equals 2 squared. So 4 to the power negative x equals 2 to the power negative 2x. We can then write our expression as 2 to the power negative 2x times 2, which equals 2 to the power negative 2x plus 1. To simplify this further, let's make a substitution. Let t equal 2 to the power negative x. Note that since t represents 2 to a power, t must be positive. So we're assuming t is greater than 0. After simplifying and substituting, we can rewrite our inequality as 2t squared minus 7t minus 4 is less than 0. Now, we need to factor this quadratic expression. We can factor 2t squared minus 7t minus 4 as 2t plus 1 times t minus 4 is less than 0. We need to find where this product is negative. A product is negative when one factor is positive and the other is negative. Let's solve for the intervals where this is true. The factor 2t plus 1 is equal to 0 when t equals negative 1/2. The factor t minus 4 is equal to 0 when t equals 4. Now, for the first factor, 2t plus 1, it's positive when t is greater than negative 1/2. For the second factor, t minus 4, it's negative when t is less than 4. Since we need one factor positive and one negative, and we know t must be positive, our inequality is satisfied when t is between 0 and 4. Since we've established that t is greater than 0 and negative 1/2 is less than 0, we can simplify our solution to 0 less than t less than 4. Now let's substitute back our value for t. Remember that t equals 2 to the power negative x, so 2 to the power negative x is less than 4. We can rewrite 4 as 2 squared. So our inequality becomes 2 to the power negative x is less than 2 squared. Since the base 2 is greater than 1, we can directly compare the exponents. This means negative x must be less than 2. Finally, multiplying both sides by negative 1 and flipping the inequality sign, we get x is greater than negative 2. Therefore, the solution to our inequality is x belongs to the interval from negative 2 to positive infinity. And there we have it. We've successfully solved the exponential inequality by using substitution and applying properties of exponential functions. Let's recap the key steps. We made a substitution to convert the exponential inequality into a quadratic, factored, and solved that quadratic, then substituted back to find the solution in terms of our original variable x. The solution is x is greater than negative 2. Let's start with our example. We need to solve the following exponential inequality. The first step in solving this inequality is to bring both fractions to the same side. We'll subtract the right fraction from the left fraction and check where the result is greater than 0. Next, we need to find a common denominator to combine these fractions. To do this, we'll need to multiply both the numerator and denominator of each fraction appropriately. Now, let's expand the numerator. We have 1 minus 2 to the power of x minus 1 minus the quantity 2 to the x minus 1. Let's simplify the numerator by combining like terms. 1 plus 1 equals 2, and we have minus 2 to the power of x minus 1 and minus 2 to the power of x. To simplify our work, let's introduce a substitution. Let's say t equals 2 to the power of x. This will help us handle the exponential terms more easily. Using our substitution, we can further simplify the numerator. We have 2 minus t over 2 minus t, which simplifies to 2 minus t over 2 minus t. Let's continue simplifying. We can combine the t terms in the numerator. 2 minus t over 2 minus t gives us 2 minus 3t over 2 all over the denominator. Now, we can factor out a common factor of 2 from the numerator. This gives us 1 minus 3t over 4 on top. Simplifying further, we get 3t minus 4 over 2 times t minus 1 times 1 minus t over 2, which is greater than 0. After analyzing the sign changes, we find that the fraction is positive when 1, t is between 1 and 4/3, or 2, t is greater than 2. Since t equals 2 to the power of x, we convert these intervals back in terms of x. Using the logarithm base 2, we get when t is between 1 and 4/3, x is between 0 and log base 2 of 4/3. And when t is greater than 2, x is greater than 1. Therefore, our solution interval is x is in the open interval from 0 to log base 2 of 4/3. And that's our solution to this exponential inequality. Remember the key steps. First, transform the inequality to get all terms on one side. Second, find a common denominator to combine fractions. Third, make a clever substitution to simplify the expressions. Finally, analyze where the resulting fraction is positive by finding critical points and checking sign changes. With these principles, you can tackle many types of exponential inequalities. Thank you for watching. Welcome to this lesson on solving exponential inequalities. Today, we'll solve a complex exponential inequality step by step using properties of exponents and a clever substitution technique. Our example is the following exponential inequality. 3 to the power of 72 times 1/3 to the power of x times 1/3 to the power of square root of x is greater than 1. Before we start, we should note that x must be greater than or equal to 0 because we have a square root of x in our expression. Now let's rewrite the expression to make it easier to work with. We can rewrite 1/3 as 3 to the power of -1. This gives us 3 to the power of 72 times 3 to the power of -x times 3 to the power of negative square root of x is greater than 1. Next, we can combine all these exponents using the property that when we multiply powers with the same base, we add the exponents. So we get 3 to the power of 72 minus x minus square root of x is greater than 1. Since we have an inequality with a base greater than 1, we can compare the exponents directly. First, let's rewrite 1 as 3 to the power of 0. Since 3 is greater than 1, the inequality 3 to the power of 72 minus x minus square root of x is greater than 3 to the power of 0 will be true when the exponent is greater than 0. This gives us 72 minus x minus square root of x is greater than 0. Now, to solve this inequality, we'll make a clever substitution. Let's set t equal to the square root of x. This will make our inequality easier to solve. With this substitution, x equals t squared. So our inequality becomes 72 minus t squared minus t is greater than 0. Let's rearrange this into standard form for a quadratic inequality. We get t squared plus t minus 72 is less than 0. Now, we need to find the roots of this quadratic expression. We'll use factoring. The expression t squared plus t minus 72 can be factored as t plus 9 times t minus 8. For a product to be negative, one factor must be positive and the other must be negative. This happens when t is between -9 and +8. But remember, we have the domain restriction that x is greater than or equal to 0. Since t equals square root of x, t must also be greater than or equal to 0. So our solution for t is from 0 to 8. Now we need to convert our solution back to the original variable x. Since t equals the square root of x, we have 0 is less than or equal to square root of x, which is less than 8. To solve for x, we square all parts of this inequality. Since squaring preserves inequalities when all values are non-negative, we get 0 is less than or equal to x, which is less than 64. Therefore, square all parts of this inequality. Since squaring preserves inequalities when all values are non-negative, we get 0 is less than or equal to x, which is less than 64. Therefore, our solution set is the interval from 0 to 64, not including 64. We write this as d equals the interval from 0 to 64. Let's review the solution process. First, we simplified the expression by rewriting 1/3 as 3 to the power of -1, and then combining all exponents. Since the base 3 is greater than 1, we could directly compare the exponents and set up the inequality 72 minus x minus square root of x is greater than 0. We made the clever substitution t equals square root of x to convert this to a quadratic inequality, which we then factored and solved. Finally, we converted back to the original variable x to find that our solution is the interval from 0 to 64, not including 64. This example demonstrates how substitution can help simplify including 64. This example demonstrates how substitution can help simplify complex exponential inequalities, turning them into more familiar forms that we know how to solve. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.